So now we have the Bohr model. We figured out the distances that the electron can be from the proton according to Bohr in these orbits that don't actually exist. And so with this information that we found, we can solve for the energy. And so the energy of a system is the kinetic energy plus the potential energy. The kinetic energy will be 1/2 mass times velocity squared, and we solve for the velocity up above. And the potential energy is going to be equal to the Coulomb potential. So minus E squared over 4 pi epsilon naught times R. So this is the potential energy of the system. And so we can then go ahead and plug in values that we found for these. So we know the velocity from above, so we get 1/2 MEV squared is the same as E squared over 4 pi epsilon naught R. And we have the potential energy, E squared 4 pi epsilon naught R. And so overall, we'll get negative 1/2 E squared over 4 pi epsilon naught R. And then we can plug in R that we solved for earlier, and we get that the energy, according to this Bohr model, is negative mass of the electron e to the 4th over 8 epsilon naught squared h squared n squared. And again, this n shows up. This is an integer, so this means we have quantization. And so we can say that the energy of the hydrogen atom, according to Bohr's model here, is quantized. And this is a consequence of the other things being quantized, right? The angular momentum is quantized, the distance from the nucleus is quantized, and consequently the energy is also quantized, since the energy depends on that distance from the nucleus. And so this solved for, this goes back to what we saw with the line spectrum, that we get these differences in energy are what shows up in a spectrum, right? As the electrons move between different energy levels, that's when we see light being emitted. And so we can solve for differences in energy are going to be equal to those energy of those photons, h nu, and then we can show that that's just going to be different integers that show up in this n squared. So me over e to the 4th, 8 epsilon naught squared h squared, and then we'll have differences in these integers, 1 minus n1 squared over 1 minus n2 squared. And so this is the Rydberg formula. So this was one of the clues that Bohr was on the right track. And so this set of constants over here, this is the same as our RH, that was 109,680 wave numbers. If we do the unit conversions, we get the same answer here. Right, so if we switch this to wave numbers instead of wavelength, or in this case, joules, where it currently is. And so Bohr's model was successful in that it does predict this formula from first principles, and this quantization of everything. Bohr properly predicts what's going on in terms of the hydrogen atom. There are things Bohr's model doesn't predict. So one of the things it doesn't predict is the hydrogen atom in a magnetic field. So if you have a hydrogen atom inside of a magnetic field, you get the lines split a little bit, and it shifts the spectrum. The other thing that the Bohr model fails completely at is the helium atom. So if we try and use the same model for a helium atom, it just doesn't work at all. And so the third thing about the Bohr model, so why it's wrong. The third thing is that it violates what we now know as the uncertainty principle. So according to Bohr, this Bohr model, we know exactly where the electron is in its orbit, right, that it's spinning around, and we also know exactly how fast it's going. We know the velocity from that equation that we had earlier. But there is a principle in quantum mechanics that states that we can't know both the position and momentum of a particle at a given time. So if we, when we do measurements on things that are quantum sized, we influence them. And so we get that delta x times delta p is greater than or equal to h bar over 2. And this is probably one of the more famous results of quantum mechanics, is that so for a particle, the uncertainty in position times the uncertainty in momentum, or since momentum also depends on velocity, the uncertainty in speed, has some, when you multiply these together, it has to be greater than a certain value, in this case h bar over 2. So in the case of an electron, say, we can't know exactly where it is and exactly how fast it's moving at any given time. And so Bohr's model violates this uncertainty principle, the Heisenberg uncertainty principle. And so that's yet another reason that this model is not correct, even though it agrees with the quantitative measurements of the hydrogen atom. It doesn't explain everything about the system. But it does get these ideas of quantization that are real, but the way it derives it is not true to what's happening in real life. So that's it for chapter 1.